Gas laws, lesson 2. In this lesson we're going to be learning about Dalton's law of partial pressures, Graham's law of effusion or diffusion, what happens when you cannot use PV equals nRT, the ideal gas law, that is, how can we account for non-ideal gas behavior. And then we'll finish this lesson with gas law stoichiometry. Dalton's law of partial pressure deals with a common container where you have a mixture of gases. Each gas within this container will exert its own individual pressure. We'll call this the partial pressure of the individual gas, as if the gas was the only gas in the container, as if it was in there alone. And if you would like the total pressure with each gas acting independently, Dalton's law simply says that you must add those individual partial pressures together to get the total pressure. Dalton's law, on the basic level, can be simply written that the pressure total is going to be equal to the pressure of the sum of the individual gases. And here we're talking about gas A, gas B, and gas C. And if the individual partial pressure of each gas is provided, Dalton's law says the total pressure in that container is simply the sum of the individual partial pressures. So if we have a common container on the right hand side with gas A, B, and C, and they're all in the same unit, in this case they're all in atmospheres, Dalton's law is very simple. We simply have to add them together to get the total pressure of those three gases in a common container. And obviously the total pressure in that container would be 6 atmospheres. In a lot of Dalton's law problems, the actual individual partial pressures are not provided. That is, you would have to calculate them using the ideal gas law. That is, PV equals nRT. And if this was the case, you would need moles of each gas, moles of A, moles of B, moles of C. And you'd have to know the temperature that the gases are at in this common container. The V would be the volume of the container, and of course R is just a universal gas law constant. So if the individual partial pressures are not provided, you could calculate the individual partial pressures with the correct information, and then add them together the way we did to get the 6 atmospheres if the pressures were provided. Notice the bottom left equation can be very beneficial. Since we have a lot of constants here, we have a common container, all the gases are at the same temperature, they're all at the same volume, the container size is the same for all the gases, R is the universal gas law constant. If you wanted to get the total pressure, and you're not interested in the individual pressure of each gas, but if all you want is the total, you can take the moles of each gas and add them together. The moles of gas A, B, and C times RT over V, and you'll be able to calculate the total pressure. So that bottom left equation can be very beneficial if all you're trying to do is get the total pressure. Let's look at an application of Dalton's law. You see in front of you that we have 3 containers. In container 1, on the left-hand side, we have nitrogen. And nitrogen in its container is exerting a pressure of 1 atmosphere. And the size of that container is 4 liters and the temperature is 150 Kelvin. In the middle container, or container 2, we have oxygen. Oxygen in its container, under the conditions stated, the 4 liters and the 300 Kelvin, is exerting 2 atmospheres. And then the third container, the one on the far right, that has carbon dioxide in it, that gas is exerting a pressure of 4 atmospheres in its container at a volume of 1 liter and 300 Kelvin. What I'd like to do is take the 2 side containers and transfer that gas into the middle container. So then the middle container will still have the oxygen, but we're going to transfer in with it the nitrogen from the left container and the carbon dioxide from the right container. So if we transfer the gases into the middle container, we'll have a mixture of gases in a common container. Each gas will exert its own individual partial pressure. That is, nitrogen in the middle container will have its own pressure, and so will CO2. Now the oxygen that's already in there is independent of whatever else we put in that container. because Dalton's law says each gas exerts its own individual partial pressure. Now this is assuming the gases are not reacting with each other. So if we want the pressure total upon transferring, we're going to need to know the pressure of nitrogen in the new container and the pressure of CO2 in the new container. So if we transfer the nitrogen in with the oxygen, notice the container size is the same. They're both 4 liters. But notice that the temperature is changing. That is, nitrogen in the new container will be at 300 Kelvin instead of 150. That is, we're going to be providing the nitrogen molecules with more energy. That is, they're going to be hitting the sides of the container more often, building up a greater pressure. So nitrogen in the new container will not exert 1 atmosphere. It's at a higher temperature in the same container size, and those molecules with a higher energy are going to be hitting the sides of that container more often, building up a greater pressure. In fact, there's a direct relationship here. So if nitrogen goes from 150 Kelvin to 300 Kelvin, that temperature is doubling. If that temperature doubles, the pressure must also double. So nitrogen in the middle container will not exert 1 atmosphere. It will exert 2 atmospheres due to the temperature change. Carbon dioxide on the right-hand container is exerting 4 atmospheres. And when we transfer it into the middle container, notice the temperature is staying the same. So we're not providing the CO2 with more or less energy. It has the same temperature. However, notice that the CO2 is going from a 1 liter container into a 4 liter container. So we're giving the carbon dioxide molecules a lot more room, 4 times the amount of room if you go from a 1 liter to a 4 liter container. But notice the temperature is staying the same, so we're giving them more room, but they still have the same amount of energy. They're still both at 300 Kelvin. So what we're going to see here is that if we give the carbon dioxide molecules more room, that is, we expand the volume and the temperature remains constant, then the pressure's got to go down. So carbon dioxide is not going to be 4 atmospheres in the middle container. It's going to be much less. Notice that if our container size goes up by a factor of 4, then the pressure's got to go down by a factor of 4. This is Boyle's law that says there's an inverse relationship between pressure and volume. So due to the volume change, carbon dioxide will not exert 4 atmospheres in the middle container. It will only exert 1 atmosphere. So if we add all the pressures together, oxygen, which was not affected by the transfer, still is going to exert 2. The nitrogen in its new container is going to exert 2 atmospheres due to the temperature change. And carbon dioxide in the middle container is only going to exert 1 atmosphere due to the volume change with the temperature not changing. And you add all this together, and if we transfer them all into that center container, then it will exert a total of 5 atmospheres. Dalton's law is very practical when we start talking about collecting gases. And whenever you collect a gas, one way of doing so is collecting a gas above water in what is called a eudiometer. A eudiometer is just simply a large test tube that reads volumes. So we're going to look at what happens when you collect a gas above water. And according to Dalton's law, if you collect a gas above water, you have 2 things that you have to consider. Obviously the gas you collected, but also there's going to be some water vapor there. When you get ready to do calculations when a gas is collected above water, what we really want to know is what is the pressure of the gas we collected, sometimes called the dry gas. When you collect a gas above water, that pressure that you're reading is called the pressure of the wet gas. That will be the pressure of the gas you collected plus some water vapor. So bottom line, a good application of Dalton's law, if you ever notice in a problem that it says something is collected above water, you've got to make sure that you subtract out the vapor pressure of water from the total pressure reading. And what this is going to give you is the pressure of what we refer to as the dry gas. When you do your calculations, you always want to do the pressure with the gas you collected or the dry gas itself. And this is very simple to do. Simply take the pressure that they've given you in the problem, the pressure reading when it's collected above water, and subtract out the vapor pressure of water at the temperature given. And water vapor pressures are temperature dependent, and you can simply look up what that value would be in a table. And in your lecture supplement, you have a very small table on page 25. You can find a more extensive table in your textbooks. So let's look at an application of Dalton's law when you're collecting a gas above water. In your lecture supplement on page 25, we're going to be doing example problem 17. And example problem 17 is really nothing more than a combined gas law problem, where we're looking at how a volume is going to change when we change both the pressure and the temperature that the gas is under. But the only discrepancy here is it says that we're actually collecting this gas above water. So if you're collecting a gas above water, the initial pressure that they're giving you is the pressure of the wet gas. So in this problem, when they collected the gas above water, the initial pressure was 753 torr. That 753 represents the pressure of the wet gas. To do calculations, we need the pressure of the dry gas. So all you have to do is look at the temperature stated in this problem, and it was 27 degrees. Go to your table of water vapor pressures and look up at 27 degrees, what is the vapor pressure of water? And from the table, the vapor pressure of water, 27 degrees, is highlighted in blue. It is the 26.74 torr. So if I want to do my calculations, I want to get rid of that vapor pressure of water. I need to subtract that out from the total pressure that was provided. So I take the 753, the pressure of the wet gas, minus the vapor pressure of water, the 26.74. This gives me what is called the pressure of the dry gas, or the pressure of the gas collected. So that would be the 726 torr. So that's what we're going to do our calculations with. So when a problem says collected above water, make sure that you subtract out the vapor pressure of water at the temperature provided. So when we collected this gas, we collected a total of 427 milliliters. The temperature reading was 27 degrees Celsius, and you always have to change this to Kelvin. So we had to add 273 to that. And what I'd like to know is what would the volume of this gas be if I actually had STP, if I had standard temperature and pressure. You may recall that standard pressure in torr is 760, and standard temperature is 273 Kelvin. So what would our new volume be if our pressure changed from 726 torr to 760, and our temperature changed from 300 Kelvin down to 273? How would that affect our volume, the 427? Two ways you can go about solving this. You can use the combined gas law, the algebraic method. That is P1 V1 over T1 equals P2 V2 over T2. You have 5 of the 6 variables. You can plug in what you know and solve algebraically for what you do not. So if we plug in to the combined gas law, the P1 V1 over T1 equals P2 V2 over T2, the only variable that we do not have is the V2. And if you cross multiply here and algebraically solve for V2, that will be the volume of the gas at STP conditions, at standard temperature and pressure. Now notice in this problem they did not give you STP conditions. You have to know standard pressure in torr 760. You have to know standard temperature is 273 Kelvin. So they stated STP conditions, but they actually did not give you the value, so you'd actually have to know those. If you actually cross multiply here and solve for V2, your final answer would be 371 milliliters. So what you see in front of you is one way of going about solving this problem. Another way of solving this problem would be using the fractional method. And the fractional method takes into account how the volume of a gas changes when you change the pressure or when you change the temperatures. So if we take a look at this from a different perspective, and we start with the 427, because that's the volume, we want to see how it's going to change. And the first thing I notice is that my pressure is actually going to be going up. Going from P1 to P2, it's going from a 726 up to 760. If you recall, according to Boyle's law, there's an inverse relationship between pressure and volume. If the pressure goes up, the volume must go down. As you can see with the arrows, I'm noting that the pressure here from P1 to P2, it's going up. But if my pressure is going up, according to Boyle's law, that volume better go down. So I'm going to have to multiply that 427 by a pressure fraction that would make that volume go down. And of course that would be the 726 over the 760. We also have to account for the temperature change. Here, the temperature from T1 to T2 is going down from 300 Kelvin down to 273 Kelvin. And according to Charles's law, if the temperature goes down, then that volume is going to have to go down, as shown by the arrows. I'm noticing that the temperature is going from 300 Kelvin down to 273. And Charles's law says there's a direct relationship between those two variables. Temperature goes down, volume's got to go down. So I've got to make that 427 volume go down because of the temperature change. So I'm going to set up a temperature fraction that's going to allow that volume to go down. And that is a 273 over 300. And notice if you multiply through by the 427, by the changes due to the pressure and the changes due to the temperature, you get the exact same answer with the algebraic method from this method right here. If you cross multiply and solve for V2, both of these would tell you that the final volume of this gas that was collected above water at STP conditions at standard temperature and pressure would be the 371 milliliters. The second gas law that we're going to look at today is Graham's law of effusion or Graham's law of diffusion. Whenever we start talking about diffusion, gases in an open container spread out to actually have the entire volume of that container. Now if we talk about a gas actually escaping through a tiny pinhole, then that is called effusion. But what this gas law looks at is the relative rates at which one gas can effuse compared to another one. The actual gas law is relatively simple. If you're comparing two gases, you can look on the left-hand side of the equality and see that it's a fraction. That is, the rate of one gas compared to the rate of the second one is going to be equal to the ratio of the molar mass of the second gas over the molar mass of the first, and you are going to have to take the square root of the right-hand side. So basically, Graham's law says the heavier the molecule, the slower it's going to be. The lighter the molecule, the faster it's going to be. So in this case, what we need are two gases, and we can compare their relative rates. How much faster is the lighter gas going to be compared to the heavier one using this equation? Let's compare the relative rates of sulfur dioxide, the SO2, to methane, to the CH4. And to be able to execute Graham's law, all you need are the molar masses of each one of the gases. The sulfur dioxide, if you use your periodic table and add it up, it has a molar mass of 64, 16 for each of the oxygens and 32 for the sulfur. Add all that up and you get your 64. The methane, the CH4, you got 12 for the carbon and 1 for each of the hydrogens from the periodic table. And all that adds up to be 16. Now, looking at these two molar masses, I already know up front that methane is going to be traveling faster than the SO2. It's lighter. Graham's law is going to let you know how much faster. The way I personally like to set these up is I like to take the heavier of the two gases, which in this case is the SO2, and I like to put its molar mass on the top part of the fraction up underneath the square root sign. That is, I want to put the 64 on top and the 16 on bottom, and then take the square root of that. If you do 64 divided by 16, 64 divided by 16 is going to be 4. The square root of 4 is 2. And if you set it up this way, where you put the heavier one on top and the lighter one on bottom, this is always going to tell you how much faster the lighter molecule is compared to the heavier one. So in this case, we're going to know that methane will travel twice as fast as SO2. Let's take a look. So if you set it up where you have 64 divided by 16, it's going to be 4. And the square root of 4 is 2. And by setting it up this way, according to Graham's law, this tells us that methane is traveling twice as fast as the SO2. Now obviously, you don't always have to put the 64 on top and the 16 on bottom. You don't always have to put the heavier one on top and the lighter on bottom. You could do the inverse of that. You could have put 16 on top and 64 on bottom. And what this would have told you is the reciprocal of this answer. It would have actually told us that SO2, the heavier gas, is traveling at 1/2 the rate of methane. So if you set it right the opposite of this, you're still going to get a relative answer. It's going to allow you to compare those two gases, but it's simply going to give you the rate of the heavier gas compared to the lighter one. But in this case, you can obviously see that methane is traveling twice as fast as the SO2. Now that we have this information, now that we know that methane is traveling twice as fast as the sulfur dioxide, we can answer the following question. If methane is traveling at a rate of 10 meters per second, then what's SO2 going to be traveling at? Well, we already know, based on the previous calculation, that methane is traveling twice as fast as the SO2. So if methane is traveling at 10 meters per second, then the SO2 is traveling at half that rate, or 5 meters per second. So once you know the relative rates of the two gases to each other, you can then answer questions like you see in front of you. Let's try one more. Let's compare the relative rates of hydrogen to oxygen. Obviously, hydrogen here is going to travel faster. It's the lighter of the two gases. Graham's law is going to let us know how much faster compared to the oxygen. Notice I have the molar masses in front of you. Hydrogen is traveling, actually the molar mass of hydrogen is 2 grams per mole, and oxygen is 32 grams per mole. And if we take the same method that we did before, where we have the heavier gas on top, the lighter one on bottom, and we divide those two, 32 divided by 2 is going to give us 16. And the square root of 16 obviously is 4. So if we visualize this, we can now see that hydrogen is going to be traveling 4 times faster than the oxygen. So the lighter gas here is traveling 4 times faster than the oxygen according to Graham's law.